Hello, welcome back to what I believe is episode 7 of Stats with Mats. It is a new week and therefore it is a new hypothesis test. This week we are going to be covering what is known as the chi-square test of association. Chi is a yet another Greek letter and symbol, which you can see up at the top if you follow my cursor. That X-looking thingy with the weird curls on two ends of the X, that is known as chi, and so throwing the squared sign on it makes it chi-square. Nothing terribly complicated there. Now, chi-square, I suspect that this will be a relief for many of you. Now, chi-square does require care and attention. There are many steps to follow here, but the math is much simpler, in my opinion, as compared to an ANOVA hypothesis test. So I think I previously said in another episode of Stats with Mats that chi-square is usually better done after a t-test and before ANOVA, because ANOVA leads very nicely into regression. But in my experience, it's better to reverse the order here for an undergraduate statistics class, because it seems to me, in my judgment, that doing chi-square right before regression and after ANOVA is a nice way to raise confidence. However, many of you, I think, have good reason to be very confident, because I reviewed and I have graded the homeworks, and I was generally very pleased with them. Like I was very pleased with the level, the quality of the work that the class had done. So please do keep that up. Okay. In the way of announcements, since it's a new hypothesis test, we will have another homework, a mini homework problem that is due on Friday. Give me a chance to see you guys actually complete the formula. So let's get to it. I'll make my dumb movie commentary kind of brief this time, because I have to say I have not seen a movie on TV that inspired me to really have a lot to say about this. So I'm going to just restate something that somebody else told to me, but I have not been able to stop thinking about it from the time since I first saw the movie. That is The Breakfast Club. So if you've seen The Breakfast Club, it's a classic 80s movie, a classic Gen X movie. And they have this beautiful, this group of very different teenagers has this beautiful coming together moment in Saturday detention. Here's the nitpick that I think is going around. They're all expelled for what they did to that library. If you just rewatch the scene where they trashed the library, they're all going to get kicked out of school for what they did to school property. And that the teacher who's ostensibly supposed to be monitoring this Saturday detention, he's definitely losing his job, even though him and a very gritty Rob Lowe ultimately develop a grudging respect for one another. So yeah, the second they show up to class on Monday, they're all kicked out of school and their futures are destroyed. Which is sad. Again, as I seem to say frequently, if that makes you sad, then I don't know, be sad. Let's talk about chi-square. So chi-square is a test of association between an independent and a dependent variable when both are either ordinal or nominal. It can be any combination of ordinal, nominal, but the key thing here is you must lack an interval level variable. Okay? So these two types of variables are together known as categorical variables. If you think back to levels of measurement, you will remember that ordinal and nominal variables classify observations into categories. They are categories where you cannot calculate a precise mean. So if I look at the example that I have here, let's think about chi-square in action. Let's say I want to understand. Excuse me. It's dusty in here. That's not a COVID cough. Sneeze, pardon me. Let's look at chi-square in action. On the left side of the left picture that I have here is political affiliation. So we know that there's clear difference there, but it's not something that can be precisely mathematically measured. And then on the right side, I have religious affiliation. So those are going to be my two variables here. Is there a relationship between political affiliation And religious affiliation, does one affect the other? So what you're going to have to do here is set up your situation, set up your two variables into what's known as a crosstab, okay? A crosstab, you will remember we've looked at a bunch of tables, is where we put one variable in the rows and one variable in the columns. And that creates intersections of independent and dependent variables where we can see what percentage of Democrats are Catholic, for example. Is that making sense so far? If not, perhaps seeing the actual table that we worked through here today will ultimately be helpful. So if we look here, is there an interval variable here? I cannot calculate an interval level mean for either one of these variables. Therefore, that's a dead giveaway that this is leading me towards chi-square, okay? So the problem here, the reason why we need to alter the hypothesis test is very simple. First of all, there's a lot of potential relationships that could be found between many categorical variables. So for example, we might believe that there is an effect of sex/gender on political, that says reference, I guess I meant affiliation, I'm sorry, effect of your sex affects what political party you support and vote for. One might also hypothesize that there is an effect of educational attainment on occupational status. Okay, let's say there we measure educational attainment in an ordinal fashion. So we're not going to just like get a mean of years of education completed. Instead, we say less than high school, some college, graduate professional degree, the same way we did in the General Social Survey lab that we were looking at back in better days when we actually could meet in the lab. And we want to see, does that affect the type of job that you get? Seems very likely to me that it would, but that is not going to easily fit into an ANOVA problem or a t-test problem. So we're going to have to opt for a different strategy. Let's say the country you were born in, your nationality might affect your attitudes. I do this all the time, by the way, with my own research, where I look at, say, French public attitudes versus German public attitudes versus Italian public attitudes versus British public attitudes. My focus on the European system and not any one European country very often leads me to try and theorize about these cross-national differences. So the European country you are born in might affect your attitudes about the European Parliament. Seems very logical. Maybe there's an effect of race, ethnicity on health status. Maybe the city that you live in has an effect on health status. That seems very likely to me, especially given the events of the last month or so. What I've been building towards here, here's the key thing. Every previous hypothesis test that we've done, all our varieties of Z and T tests and the ANOVA test, we relied upon an unstated assumption. We relied upon believing that we had a valid mean. Well, let's call back to the example I had on the last slide, the effect of, let's say the effect of religious affiliation on political preference. There is no mean that we can calculate there. So now, in the absence of having a valid mean, we're going to have to do something creative. We're going to have to look for a different way to test whether there's an association here. And that's going to start by trying to theorize about what a table would look like in theory if there was never any association between the two variables. Okay, so let's revisit our crosstabs. In the way of vocabulary, I would like you to conceptualize each square as a cell. Okay, so each square, then each cell, is the intersection of two variables. So let's look at the top left corner of this table here. I have in my columns religious affiliation. And I have in my rows my political preference. So the very first top left cell is the intersection between Christian and Republican. So if I'm looking at that, I can see that 126 of people in this overall sample, of which there are 518, if you quickly look at the bottom right, back to the top left, I can see that 126 people are Christian and Republican, and that comes out to 58.3%. 58.3% of what? This is why we looked at row and column percentages all the way back in like week 3 or something. 58.3% there is referencing the column percentage. So if you follow along with my words on the slide here, we want to put the independent variable in the columns and the dependent variable in the rows. The independent variable is the thing that we hypothesize will have an effect on something else. The dependent variable is the thing that's being affected by the independent variable. So here, because I have my religious preference, and granted, I'm look, in the interest, I realize that there are certainly more complicated political preferences than just saying Republican, Democrat, Independent. I realize that are far more religious religious affiliations than just Christian, Muslim, Jewish. But in the interest of keeping your first time a little bit easier with Chi-square, I just reduced this to a 3x3 crosstab, which I think makes a lot of sense. So that 58.3% now, I am theorizing downward to the column. Because I've set it up this way, I'm hypothesizing that religion has an effect on political preference, not the other way around. And because I'm operating with a column percentage here, notice how the columns sum to 100%. That's key here. You have to set this up in such a way that everything sums to 100% in the columns. So 58.3% of Christians are Republican. I'll repeat that to make sure we're all on the same page. 58.3% of Christians are Republican. That's 126 of the 216. Now, 71 or 32.9% of Christians are Democrat, and 19 or 8.8% of Christians are independent. Sum those three together down through the column of Christian, and we get to 100%. Now, to go through the rest of the cells, all religious affiliations are operating on the same logic of column percentages. So 36.3% of Muslims are Republican, 55.4% of Muslims are Democrat, and 8.3% of Muslims are independent. And finally, for the last column, 51.5% of Jews are Republican, 28.4% of Jews are Democrat, and 20.1% of Jewish voters are independent. Now, the cell value, as I've been going through here, the cell value becomes the proportion of each column, right? The proportion of Christians falling into the row group category. For the first cell, that would be Republican. Make sense so far? All right, this is our real data. This is the data that we are going to be testing. Is there a relationship? I can eyeball this and see that, all right, it looks like there's a greater proportion of Christians that are Republican than Muslim, than certainly Muslims and also Jews as well. But as I hope we've learned right now, we can't eyeball these things. We have to actually theorize and test the hypothesis rather than just say, yeah, clearly there's an eye test that has been passed here. Okay, so this is our crosstab. We're going to call this a 3x3 crosstab. 3 rows and 3 columns, 3 religious groups and 3 political categories. Now, there is a column here. There's a fourth column here that I have yet to really discuss, and that is the total column. That's about to become really important. I didn't discuss that on the last page because I just wanted us to get comfortable with marginals. However, let's look at the total. There's 518 people in this sample. 49.4% of any religious affiliation are Republican. 39% of any religious affiliation are Democrat, and 11.6% of any religious affiliation is independent. And that's about to become the key thing we're comparing to. The trick with chi-square is understanding I'm not really comparing the marginal percentages for Christians to Muslims and Jews. I'm not comparing within the groups to each other. I'm comparing each group to its total percentage. And what that will tell me is how different this would look if there was absolutely no effect of group affiliation on the dependent variable. Okay, so that might make a little more sense if we take a look at visually what the data would look like if there was no association between the two variables. So again, actually, let me go back here real quick. Take a glance at the total column, 49.4%, 39%, 11.6%, and then obviously the intersection of total and total would be 100%. If there was no association between the two variables, we would expect the same proportion of people who are Republicans in the overall population would therefore be represented in an equivalent fashion within each subgroup. So take a look at what you see here on this graph here. This is a hypothetical no association variable. There are definitely differences in political affiliation, but 49.4% of everybody is Republican. And 49.4% of all Christians are Republican. And 49.4% of all Muslims are Republican. And 49.4% of all Jews are Republican. Do you see what's going on here? In this type of situation, the percentage of Republicans in the overall population mirrors the percentage of Republicans in each subpopulation. And the same thing's happening with Democrats. The same thing is happening with independents. So if the exact same proportion of Christians, Muslims, and Jews are Democrat, as we observe in the overall population, there is absolutely no effect of the religious affiliation variable because the same thing is observed within the subgroup. So all you're doing is, if you see this type of data, all you're doing is throwing a condition on it and saying, I want to divide this into 3 religious subgroups, but it does not change the overall proportion of Republicans, Democrats, and independents. Okay? So looking at the 2 elements of the sample data here, if there's no relationship exists, then no difference is observed across the categories. It would all be happening at the level of political affiliation, not at the level of religious affiliation. So put another way, let's compare the top table, which is a hypothetical no association, to the bottom table, which is our actual data. If there is no association between these 2 variables, I would expect 49.4% of Christians to be Republican. However, what I actually see is that 58.3% of all Christians are Republican. If there was no relationship, I would expect 39% of all Christians to be Democrats because that's what the total marginal is. In fact, what I actually see, though, is 32.9%. And looking at the bottom, I would expect that 11.6% of Christians were independent, assuming no relationship between the 2 variables. But what I actually see is 8.8%. So we have some differences. Are they significant? Are these relationships statistically significant, or do we lack the evidence to say that this might just be that this actually is significant? Maybe this is just the result of sampling error. Maybe this is just the result of weird stuff that happens when you get a sample of the overall population. So let's take a look at the formula. The chi-square formula is as follows. The summation of f observed minus f expected squared divided by f expected. So the summation, put in the English language, it is the summation of each cell's observed frequency. That's given to you. Minus the expected frequency. That you have to calculate. Squared and divided by expected. So in the formula here, FOBS, let that stand for frequency observed, and it will be calculated for, or it will be given to you for each cell. Let F expected stand for the predicted frequency for a given cell. Why don't I get rid of that annoying typo? I'm sorry. And that has to be calculated by predicting what would be the expected frequency. What would you see if there was no relationship between the variables? and the proportion within the subgroup mirrored exactly the proportion in the overall population. And calculating that's simple, but you have to keep your head like very closely in the game to avoid making a silly math error, which all of us are capable of. I feel like I say that a lot, but that happens. Actually, and as an aside, while you guys are maybe internalizing chi-square, the other day I came to a latently disturbing observation where I was sitting at my kitchen table writing out the answers to the next math problem that I wanted you guys to do for homework so I could have it uploaded. And I came to the realization that I just look at my life right now. I don't go into work. I'm not allowed to go to the bar. I have to ask somebody for permission if I want to go outside, and I'm doing math at my kitchen table. I am in middle school all over again. And that made me, that was not a good feeling. I really hope we can get on top of this freaking virus and get back to normal, but that will take a significant social and public health commitment to make that happen. Anyway, so we'll have to calculate the expected frequency. Now, following the order of operations, we will subtract that expected frequency from the observed frequency. We will then square it to get rid of our pesky negative. So this can be summative. Then we divide by that same expected frequency we just calculated. And finally, we will sum that across all cells that we have in our table. So hearkening back to our example here, we have 3 religious affiliations and 3 political preferences. Therefore, we are going to have to do this 9 times to reach the summation. Now, the way I encourage you to set this up is to follow the order of operations. So, and before I get to that, similar to ANOVA, because as you can see with the squared property there, this is going to only be positive. Therefore, ANOVA is a no-tailed test. Chi-square can only ever be positive. Why can it only be positive? Because you do not have any possibility to maintain negatives after the squaring happens, okay? So no-tailed test. In a no-tailed test, we will reject the null hypothesis in a situation where our observed chi-square is larger than the critical chi-square. Okay, I'm ready to move on. Hopefully you are too. This is essentially what we need to be doing. Comparing the observed proportion for each category to the expected proportion. But we're going to need to actually calculate the value, the expected raw value, in order to make this formula, in order to make this test work. But this is just the 2 tables merged, where I can see that the observed proportion of Republican Christians is 58.3%, and I'm expecting 49.4%, because that's what I observe in the total category, in the total column. I observed 36.3% of Muslim Republicans when I'm expecting 49.4%. I observed 51.5% Jewish Republicans when I'm expecting 49.4%. So you don't need to write this down, because it's very much, it's just a merging of the 2 tables and the 2 categories. If you're wondering what I'm doing there, my chair is very old. This is the chair that got me through grad school, and it's not very functional. It constantly lowers itself. Anyway, let's move on to our hypothesis test, because we're going to have to do the same 6 steps as we've done for anything here. Step 1 is, what do we know? This is easy enough. I just have to list what my independent variable is and my dependent variable. That's important. You have to know which is affecting what. What is affecting what? Make sense? So my independent variable here is religious affiliation. And my dependent variable here is political affiliation. Therefore, I am hypothesizing that there would be an effect. What religion you are is the thing that's affecting and influencing and creating a pattern within your political beliefs and political affiliation. And then I just have to write the N. I'm doing this with a sample of 518 individuals. That will always be a given. In fact, everything in the knowns is always a given. So what are my hypotheses here? Again, because this is a no-tailed test, I don't have to worry about directions. I don't have to worry about less than or greater than within the cells, even though that will happen. Like some cells will be perhaps greater than their expected frequency and some will be less than their expected frequency. Nevertheless, the hypotheses only care about difference. So, null hypothesis. There is no association between religious affiliation and political preference. Can I write this mathematically? No, I cannot. Because if you remember, with all our previous hypothesis tests, we were using X bar to stand in for mu. We were using means in samples to stand in for population means. The whole reason we're doing a chi-square here is because we do not have a valid mean that we can rely upon anywhere ever. So therefore, you have to write out there is no association between religious affiliation and political preference. You cannot do this mathematically. And my alternate hypothesis is going to be the opposite of the null. There is an association between the religious group and the political preference, or religious affiliation and political preference. Null, there is no association. Alternate, there is an association. Okay, so steps 1 and 2, I think we as a group are getting pretty darn comfortable with that. Step 3 and 4, we have to set our alpha level and determine our critical statistic. So as I do with pretty much every first example that we do you guys feel good about 0.05? I feel good about 0.05. So let's go ahead with 0.05. Now, for the critical region, we are now going to have a different formula for determining the degrees of freedom. The degrees of freedom for a chi-square formula or chi-square test is R minus 1 times C minus 1, where R simply equals the number of rows and C equals the number of columns. You will remember that in our particular problem here, we have 3 religious preferences and three political preferences. So number of rows, R equals 3. Number of columns, C equals 3. So what we're doing here is 3 minus 1 times 3 minus 1, or 2 times 2 equals 4. So the degrees of freedom here are 4. And that's all we're going to need. We're going to need the degrees of freedom and your alpha level to figure this out. So I need you to go into your stats packet to the very last page, and you will see Appendix C, distribution of chi-square. Please look up this table. You will need to find the alpha level in the columns. Go to 0.05 and then move downward until you reach the row for degrees of freedom of 4. To determine the critical region here, I see it. I'm looking right at that. But if your degrees of freedom falls between 2 listed values, once again, use the smaller degrees of freedom. If your degrees of freedom is greater than 30, which I can't imagine it ever would be, that would require a tremendous amount of hand calculations, you simply use the last listed value. So based on the distribution of chi-square that you see here, for 0.05 comma df of 4, what you should, I'll pause for a second if you haven't looked it up yet. Okay, if you're ready to continue, The degrees of freedom of 4 and an alpha of 0.05 should have given you a critical chi-square of 9.488. Because we're doing a no-tailed test, our value has got to be greater than this, right? So if it's cool with you, let's move on to calculating the observed chi-square. So the fact that I have a clear order of operations embedded in this formula, what I'm going to do is I'm going to set up a table that will allow me to do this step by step in order to get the right answer. So the summation of frequency observed minus frequency expected squared divided by frequency expected. Frequency observed is a known value. It's given to you in the problem. So the first thing I'm going to want to do here is calculate the expected frequency. Second, I will subtract that from frequency observed because it's within my parentheses. Then I will square that value following the order of operations, and then I will divide that by the expected frequency I calculated first and foremost. And then at the end, I sum across all 9 cells. So the way I have set this up here is very much how I encourage you to set this up going forward. Let me actually move this here. So if you look at what is embedded here in the table now, I've just added some cells here that will allow me to follow coherently the order of operations. I first need to calculate frequency expected, then subtract it from frequency observed, then squared and divide by frequency expected. Now, how do I get the expected frequency? I suspect many of you already know how to do this. How do you get the value for anything? How do you get the relative frequency for anything? Well, you multiply the percentage by the raw value. Easy enough. So what we're going to want to do here is take the total percentage for each row and multiply it by the total raw value for each column. And that's FE. That's the frequency expected. So what does that look like in practice? Subtract FE from FO, and finally square it and divide by FE. So let's get to work on that. To first calculate frequency FE, I need to be taking, you see the arrow up here in the top right? I need to be taking 0.494, and that was something I did not have to calculate. It was given to me, but I might have to calculate it in future assignments. I need to take 0.494, and I need to multiply it by 216. Put another way, I need to multiply the total percentage of Republicans times the total raw value of Christians. And that will give me the raw value that's expected if 49.4% of Christians are Republican. I'll walk through that one more time here. I take the percentage, the total percentage of Republicans in the overall sample, and multiply that by the total raw value of Christians. And that will give me, by multiplying 0.494 times 216, that will give me the frequency expected for Republican Christians if there was no relationship here. The frequency observed is 126. But when I do this, I get a frequency expected of 106.704. Am I done? No, of course not. So in your notes, I would like you to try your hand at this. I will pause momentarily, but also pause the video if you need to go through this. Because going forward, how do I then apply this to the Muslim variable? Well, I'm going to take that 0.494 and I am going to then multiply it by 168. And doing that will give me an expected frequency of Muslim Republicans of 82.992. Think you see where this is going. What do I do with the Jewish column? Well, take 0.494 and multiply it by 134, and that will give me 66.196. And that's great. Now I have my expected frequencies for every type of Republican: Republican Christians, Republican Muslims, and Republican Jews. Going forward, now I just have to now do the same thing, except I have to make sure I'm using the correct total frequency, or the correct total relative frequency for each group. So in order to get the expected frequency for Democrats, I now use the total relative percentage of Democrats in the overall sample. So now I'm multiplying 0.39 times 216, 0.39 times 168, and 0.39 times 134. And that will give me the percentage of, that will give me the value of expected Democrats who are Christian, Muslim, and Jewish respectively, if there was no relationship between these two things. And now, I think you see where this is going. In order to get the expected frequency for the independent cells, I have to take 0.116, multiply that by 216, 168, and 134, and that will give me the expected frequency for independent Christians, Muslims, and Jews, respectively. So I'll pause here for a second. Please pause the video. Try your hand on finishing out that part of the table. All right, so here's what I got. My frequency expected for Democrat Christians is 84.24. My frequency expected for Democrat Muslims is 65.52. And my frequency expected for Democrat Jews is 52.26. Moving on to my independents, no problem. My frequency expected for independent Christians, 25.056. My frequency expected for Muslim independents is 19.48. And the final frequency expected, 15.544. And what you have there now allows you to move forward with the rest of the problem. So you can see the reason why I've set up the table like this is because each step is embedded within the table. Now I need to take frequency observed and subtract from it frequency expected. So if we look at our first marginal, I need to take 126 and subtract from it 106.704. And doing that will give me 19.296. I will pause there for a second, and I'd like you to finish out the rest of the table. Okay, so moving on, what you should have gotten is a table that looks like this. Negative 21.992, 2.804, negative 13.24, 7.48, 14.26, negative 6.056, negative 5.448, and 11.4 5, 6. That is the difference. That is each expected frequency's value. That is the deviation of each expected frequency from its observed frequency. So if it's positive, then that means that the observed frequency is greater than the expected frequency. If it's negative, it means that the observed frequency is less than the expected frequency. What do I have to do next? Square it to get rid of negatives and divide by the expected frequency. So once again, I'll pause here for a moment to let you guys finish out the table. In the first marginal, that gives me a chi square for that cell of 3.4894. I'd like you to finish out the remaining 8. And now your table should look something like this. 5.8276, 0.1188, 2.0809, 11.5255, 3.8911, 1.4637, 1.523, and 8.2931. What's the final step here? Well, that gives me everything I need in order to calculate chi-square, which is simply the summation of everything that you just did. So sum all your observed chi-squares together. What you see here at the bottom is each cell's chi-square and is now being summed by adding all 9 together. So the summation of these 9 values, I'll give you a minute to calculate it. 38.2131. It's a big number. Well, what does that mean? Well, we have to call back to the critical value that we looked up in Appendix C. So I ask you, does 38.21 fall beyond our critical value of 9.488? Is 38.21 larger than our critical value of 9.488? You better believe it is. We've done it. So therefore, we reject the null hypothesis with 95% confidence, and we conclude that there is a statistically significant relationship between religious group and political party affiliation. We reject the null hypothesis because our critical value was less than our observed value. 38.21 is much greater than 9.488. Okay? We did that together. I'm proud of us, and I hope you're proud of yourself as well. Okay? So we will revisit some other issues. We will continue to work through a new chi-square problem with some added bells and whistles on Wednesday. But for now, I certainly hope you're feeling confident with chi-square. I don't think the logic is difficult to understand. I don't think it's nearly as tricky as ANOVA is. But as you can see, there's a decent amount of wrench work that you have to put in, and there's a decent amount of small calculations that you have to put in. So I will say what I seem to have said all semester: the details matter. Take the details seriously. The students who work slowly, the students who work carefully, and the students who check their work are going to be the students who earn full credit on any assigned chi-square problems. Okay? Thank you very much. Have a great next couple days. I'll catch you again on Wednesday. Bye-bye.